All right, good morning. Let me share the folder for the week. So in the schedule for the week, I've updated that with what we did like yesterday and today. I put the Zoom recordings from yesterday or from Monday and yesterday in there. And so if you need to, review any of the things that we went over or want to see more examples, they're there. Today I want to go over the hydrocarbons practice one worksheet and then show you about other ways that we name different types of hydrocarbons, and then with some good examples. And then there's another practice paper with hydrocarbons, including like cyclic rings, hydrocarbons, that's in there for homework. So in the folder, everything's kind of like in chronological order. From Monday, this was the notes for how to name acids and the notes outline, and there was that exit slip. There was the practice, and we went over that yesterday. And then these were the notes from yesterday about naming straight chain hydrocarbons. And these are the practice problems I want to go over right now. And then these are notes for naming other types of hydrocarbons. And there's a practice that you can do for tomorrow. So that's what the plan is. Um, the formatting in this one's a little bit messed up. It's difficult sometimes. I mean, like whenever you view a PowerPoint in PowerPoint, it always looks right. But Schoology kind of messes things up a little bit. And in some of them, and I even tried to fix it and move the diagrams around. Unfortunately, like whenever it's viewed in Schoology, it'll like move the stuff around a little bit. You'll see what I mean. Let me see if I can find one of them. So the best way, if you're having trouble seeing the image, yeah, like here it says like these two are both propene, one propene, but it kind of gets cut off, and sometimes the image is over top of the thing. And I've tried to change it a couple different ways. If you just download it, then you can view it offline, and then whenever you view it that way, it will look correct. It should look correct. Just Schoology doesn't make it look so perfect. You can also try to go full screen, because if you try to go full screen, it'll look all right. Because some students have been like, I'm having trouble seeing this and can't get it to look right, and I guess that's probably like the best thing I can suggest. Uh, I don't know. Okay, so these the naming hydrocarbon practice that I ask you to give it a try, um, and you can always refer to in the notes like the order of uh, the lengths of the chains of hydrocarbons and stuff. And I want to say some things about a couple of these so you can see like how they end up going and why they're in the shapes they're in, because there are different ways to draw and describe the names for different types of hydrocarbons. So actually, I'm going to switch to a different thing. This thing here, the like the tablet I can write on. All right. So in that practice, there are different ways to write formulas and see the names for different compounds. One thing that a couple things that could help you. One of them is to try to write the formula for the compound. And what's always true for hydrocarbons is we always start off with the carbon and the number of carbons and then the number of hydrogens. So like in number one, there are three carbons here in a chain. We call that a three carbon chain. And because there are three carbons, the formula is C3. And then when you count up the number of H's, it's H8. And because there's a three carbon chain, it has to be this prop something. And so two different ways you can come up with what the name is. One of them is when you look at the bonds, they're all single bonds. And because they're all single bonds, it must have the name of an alkane, because alkanes have single bonds. So because there's three carbons in a chain and it's an alkane, it's just propane. The other way you can know that it's an alkane or ends with an ane is based upon the chemical formula. The generic formula, here, I'll write it over here. I'll write it further over here. For alkanes, is the generic formula is CX H2X plus 2, meaning however many carbons there are, the number of hydrogens is double that plus 2. And in this case, you can see that if it's C3, it's got to be H2 times 3 plus 2. And 2 times 3 plus 2 is 8, C3H8. So the chemical formula is in accordance with what the naming rule is for alkanes. But anyway, that one's pretty easy. 3-carbon chain, it's an alkane because they're all single bonds. It's called propane. In number 2, if you write the formula, it's C4, and then you count the number of hydrogens. There's 8 hydrogens, H8. Now that can't be an alkane because it wouldn't follow this formula. You can tell that real quick because, well, if 3 carbons for an alkane has 8 hydrogens, well, it can't be possible that 4 carbons would also be 8 hydrogens. But the number of hydrogens is exactly double the number of carbons. And that's following the rule for alkenes. So for alkenes, the generic formula is CXH2X. Or in this case, because it's C4, it's H8. So it follows the rule for an alkene. So you have 4 carbons in a row, which is bute, and then it's an alkene, so it's butene. The other way you know that it's an alkene is alkenes have double bonds. And you can see that there's a double bond here on this first carbon. So there's 2 clues. One clue is double bond. That makes it an alkene. And then when you write the formula, it follows the rule for an alkene. In this one here, it's C3 and then H4. There's 3 carbons and 4 hydrogens. Following the rule for alkynes, that's CXH2X minus 2. And here we have 3 carbons, and then it's hydrogen 2 times 3 minus 2. Well, 2 times 3 is 6, minus 2 is 4, or C3H4. So it turns out this formula actually follows the generic equation for how alkynes work out. And there's 3 carbons in a row, so it's propyne. The other way you know that is there's a triple bond. And because there's a triple bond, it's got to be an alkyne. So the rules go, alkanes, they're all single bonds. Alkenes have double bonds, and alkynes have a triple bond. And in all these cases, these double and triple bonds are all on carbons that are at the end. And that's not always true, and I'll show you exceptions to that today. Anyway, so the number 4, like real quick, we got 5 carbons in a row. So it's C5. Oops. And then there's 10 hydrogens. So it's C5H10, and there's a double bond over here. So that formula follows the rule for alkenes. And there's a double bond, which means it's also an alkene. So there's 5, which is pent. Ene. So pentene is the right name. Now in number 5, you see this thing makes a bend here, and that really doesn't matter at all. It's 4 carbons in a row. So whether they're all drawn in a straight line or whether it makes a bend, it totally doesn't make a difference at all. There's no bond between these hydrogens. And in fact, this would actually not be exactly what the molecule would look like, but they're all single bonds and there are 4 carbons. So that's butane. That's the molecule that's used as a fuel in like lighters. And again, the formula is going to be C4 H10, because we got, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, C4H10, we're good. Number 6, there's 2 carbons, so that's eth, and it's a triple bond, ethyne, and the formula is C2H2, and that follows this rule for alkynes, because if it's C2 and then H, if it's 2 times 2 is 4 minus 2 gets you 2. So that one's called ethyne. And number 7, we've got 4 carbons in a row. So that's bute. and then it's got a triple bond. So butane, C4, H6. And that follows the rule for the formula for the naming, for the formula, in that if you have 4 carbons, 2 times 4 is 8, 8 minus 2 is 6. So butane looks good for that. And number 8, this is actually like what the shape of the molecule looks like in cross-section. We're going to work with the molecular model sets when or if we come back to school, and you'll be able to see how these molecules actually fit together using what we call the ball and stick model. And I'll illustrate that to you later this week anyway. But you just look at the number of carbons that are in a row. So it's 1, 2, 3, 4, 5, 6. 6 carbons is hex, and they're all single bonded. That's hexane. And again, it's going to be C6H14 when you count up the number of hydrogens. So like there's 6 up here and 6 down there, that's 12, and then 13, 14. And that follows this rule, because if you got 6 carbons, then when you put 6 in for the X, 2 times 6 is 12, and another 2 gives you 14. So that's how those go. Those are the right answers for those formulas. If you have questions or you want me to go over one in a different way or something, you can put it in the chat. I'll take a look. I'll see it. All right, then the problems toward the bottom, or the rest of them, 9, 10, 11, 12, 13, 14, 15. We want to know formulas for these. So formula for nonane, non means 9, and alkane is a 9-member alkane. So alkanes go, it's C9, and then it's H, 2x plus 2. I'll just show kind of like how the math goes here. 2 times 9 plus 2 is 20. So it's C9H20. It's 2 times 9 is 18, and 18 and 2 is 20. All right, so a hydrocarbon with 2 carbons and a double bond. I'll just draw that. So we got 2 carbons with a double bond, but then there have to be some other hydrogens. And it turns out that this double bond represents 2 electrons from this carbon and also 2 electrons from that carbon. So it turns out that there's a hydrogen here and a hydrogen here, one like this and one like this. If I do it as like a Lewis structure, I've got a carbon with its 4 electrons. I'll put another carbon over here with its 4 electrons, and then hydrogens. Put one up here, put one here, and one here. So in color code are the electrons that belong to each of the carbons. They're the valence electrons. Hydrogens each have 1 valence electron. Each carbon has 2 valence electrons. And this double bond is represented as 2 pairs of electrons being shared by the 2 carbon atoms. So that's a way that the Lewis structure is drawn. But based upon just the written description, you can figure it out too. We've got a hydrocarbon with 2 carbons, so it's C2. And if it has a double bond, a molecule with a double bond has to be an alkene. So we got to follow the rule for the formula for an alkene, which is however many carbons, there's twice as many hydrogens. So that looks like C2H4. And building the molecule up from the Lewis structure or from the stick model, it looks like we got to have 4 hydrogens to go with those 2 carbons to satisfy the octet rule for the carbons, and for each hydrogen to have its 2 valence electrons. Same with like number 11, an alkene has to have double bond as well, an alkene with 5 carbons. So it's C5, it's going to be H10, because for an alkene, it has twice as many hydrogens as the number of carbons. So just C5H10. And it turns out that when you draw that structure, I've got a carbon that's double bonded to another carbon, and I got to have, let's see, so there's 1, 2, 3, 4, 5. I got a double bond on this carbon here. So the other hydrogens are going to be one here. There's got to be a hydrogen, and just kind of fill them in. Another way to see it is every carbon has to have 4 lines coming off of it. And if the hydrogen doesn't have 4 lines coming off of it, then you need some more hydrogens. So I can draw it like that. I've got 1, 2, 3, 4, 5 on the bottom, 3 on the top, 1 here, 1 here. So every carbon has 4 lines coming off of it, and every hydrogen has 1 line coming off of it. That's always true. There's no exception to that. Well, there can be exceptions to that, but for alkanes, alkenes, and alkynes, there are no exceptions to that. Anyway, an alkene with 10 carbons, or sorry, alkane with 10 carbons is C10. Oops, I gotta back that up. C10H22, because that is decane. So this one here is decane with 5 carbons. This was pentene, and a hydrocarbon with 2 carbons and a double bond. That's ethene. C4H4, all we're doing is trying to just name these. So this has got to be an alkane. Well, there's no such thing as an alkene or alkyne with 1 carbon. That doesn't make any sense. The only thing that has 1 carbon is just methane. In other words, there can't be methene or methine, because in order to have double and triple bonds, you have to have 2 or more carbons anyway. So then here, C2H4 or C2H6, that follows this formula for alkanes as well, because if you have 2 hydrogens and or 2 carbons and you put a 2 in here for where the hydrogen is in the formula, that's got to be ethane. In other words, that follows the equation C2H, 2 times 2 plus 2. 2 times 2 is 4 plus 2 is 6. But C2H4, the number of hydrogens is only double the number of carbons. That follows the equation C2H, 2 times 2. So that's ethene. The number of hydrogens is a ratio of the number of carbons is the big clue as to whether or not it's an alkane, alkene, or alkyne. But you can also draw formulas for them. So, for instance, in number 14, if I try to draw that equation or draw that formula or draw the like model for it, I can have 2 carbons that are single bonded and then have these hydrogens coming off of it, and it fits 6 hydrogens, so that we've got 4 bonds coming off each carbon and 1 bond coming off each hydrogen, and that's a total of 6 hydrogens. But here with number 15, I'm going to kind of overlap this. If I draw the 2 carbons in a row and then draw 4 hydrogens, kind of equally distribute them, you'll see that that little kind of rule about having 4 lines coming off each carbon is not satisfied yet. I've got the 2 carbons bonded to each other, and I got some 2 hydrogens over here and 2 hydrogens over here, but each of these carbons only has 3 lines coming off of it. So there must be a double bond that exists here, or those 2 carbon atoms each share 2 electrons with the other carbon, or there's a total of 2 pair or 4 electrons shared between the 2 carbons. And this name, ethene, means that it must be an alkene, and alkenes have double bonds. So it's like a bit of a puzzle. You got a bunch of different pieces. You've got these chemical formulas. That's one clue. You got the ideas about Lewis structures, which is another clue. You got this model where you've got lines coming off the atoms where each line represents a pair of shared electrons. That's another clue. You've got the way that the equation has to work to satisfy the ratio of carbons to hydrogens. And then you've got the naming scheme as to like what the number prefixes are. So there's a bunch of different ways to get to the answer, and they all have to match up, and they'll all match up perfectly. A thing I'll say about all of these that I did as examples and were in the homework is you'll see that these double and triple bonds are always on the ends of the molecules, meaning this double bond is here. I didn't draw it in this location or this location. it can be over here, which is perfectly okay, but the double bond has always got to be on one of the ends with the naming scheme that I just showed you. The double bond doesn't have to be at the end, and that's a new thing that I want to tell you about today. The position of the double bond can make the name change to be something different. So anyway, and all these videos are always recorded, but I'll post the answers to these separately as a separate document on the Schoology page, like as soon as, I don't know, well, about 10 o'clock or so. But it's in the recording for today, which I'll try to get up pretty quick. It'll probably be like 9:45 or so, maybe 10 o'clock. Okay, so in the folder for this week, there's the second to last document is a PowerPoint slide deck that says like naming hydrocarbons part 2, and there's some information in there that's generic about alkenes and alkynes and alkanes, but we're going to focus on alkenes and alkynes, which are double and triple bonded carbon chains, and then cyclic or aromatic carbons groups. Okay, so here's some things that are true for alkenes and alkynes. If the double bond or triple bond is on the first carbon, then there's no number needed in the name. Well, what that means is, so for instance, if you have propene goes that there's 3 carbons, so I can have my 3 carbons. Actually, I can't use prop. I got to use bute. Doesn't make sense to start with there. Butene. So for butene, if the double bond is on the first carbon, which means there's a double bond on this very first one on the end, and that first carbon can be on this end or it can be on the other end. It makes no difference whether it's on the left or the right. That's completely irrelevant. But whenever we number these carbons, if you're going to number the carbons in the chain, this is carbon number 1, 2, 3, and 4. If you number the carbons in this chain, you don't start with number 1 over here. You start with number 1 over here, because the numbering goes from the most complex or the greatest number of bonds to the least, or to the part of the atom, part of the molecule with single bonds. So the carbon chain is not always numbered from right to left. It's numbered so the special bond or the double or triple bond is on the lowest numbered carbon. In this example of butene, this is the first carbon, but this is also the first carbon. All the time, we don't use numbers in the name if it has to do with a bond being on the first carbon. And with a number in the name, we haven't even done that yet. I'm about to show you that. So with the generic name butene, it can either be this or it can be this. And I haven't shown the hydrogens, but that would be like this. We don't always necessarily show the hydrogens because it's assumed that there are hydrogens. And I'll tell you about that like as we go along. Anyway, so this is called butene, and you can also draw it the other way where you've got the double on one end and the single on the other end. Let's see. Oops, I got one too many. I had one too many hydrogens. There's only one hydrogen on that carbon. So the number of carbons is given with a dash, and then there's a name. And I'll show you what that means here in just 1 second. So these are rules that apply to naming alkenes and alkynes. I guess what I'm trying to say is what I showed you about yesterday is about naming alkenes and alkynes, just as like butene or butine or octene or octine or something like that, where the double bond or the triple bond is on the first carbon. Okay, so here's some examples. This is one way to draw propene. So propene has a 3-carbon chain and there's a double bond on the first carbon. But there is really no such thing as, drawing it incorrectly or having a double bond somewhere in the middle of the molecule. Because if there are only 3 carbons, you can either have the double bond on the left or show the double bond on the right. And the name of this is always just propene, but the 1 dash refers to which carbon the double bond is on. So in this case, if you were to write 1 propene, it's redundant to just say the word propene. And what I'm saying there is, because if you number these carbons, like carbon 1, 2, and 3, if you were to, instead of draw the double bond on carbon 1 going to carbon 2, if instead you put the double bond over here, that also automatically makes you want to number from right to left. So the first carbon is the carbon on the left anyway. There's no other way to have propene besides having a double bond between one of the 2 sets of carbons. So it's always just propene. 1 propene is also kind of okay, but that's like kind of redundant or unnecessary. A better example, so when you get into complex examples, that's where the examples make more sense. This number 2, 2-butyne, refers to butane that has the triple bond on the second carbon. There's another way to write that equation, and that's if I draw it like in the stick model. I can draw it like this. It's a 4-member carbon, but instead of the triple bond being on the end carbon, like here or here, with the hydrogens coming off of it, hydrogen, hydrogen, hydrogen. I need some other hydrogens here. So this is also a way to see it as the atom and stick model. I got 3 carbons coming off the first, 3 hydrogens coming off the first carbon, 3 hydrogens coming off the last carbon, and then the triple bond is in between instead of on the end. If the triple bond were on the end, it would just be called butane. So for instance, when I showed you yesterday, you make the molecule in this fashion, it still has the same number of hydrogens, like this. Let's see. This is still just butane, but it's not necessary to put a number in front of it. You wouldn't have to call it 1-butyne. It's redundant because if this is carbon 1, 2, 3, and 4, the triple bond is already on carbon 1. Or if you were to have the triple bond over here, this would just become carbon 1. So it's just called butane. But now the triple bond is inside and not on the end carbons. And when you number these carbons, it's carbon 1, 2, 3, and 4. And the triple bond is between carbons 2 and 3, but it's whichever of the carbons has the lowest number is what you use. So it's just 2-butyne. You can also see that if you were to number them from right to left, 1, 2, 3, and 4, that the triple bond would still be coming off of carbon number 2. So there are really only 2 kinds of butane. There's just butane, or 1-butyne, and then there's 2-butyne. There's no such thing as 3-butyne because there isn't like a 5th carbon atom. In this example, if you look at the carbon chain, there's 6 carbons in a row. Here, this is like carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. And it's because there's 6 carbons in a row, it's hex. And because there's a double bond, it's ene. And because the double bond is not on carbon 1 or on this end carbon or that end carbon, but it's on carbon 2 going to carbon 3, it's just called 2-hexene. An example of what 3-hexene would be to have carbon, another carbon, and this is the 3rd carbon, and that's where you have the double bond. and then a carbon and a carbon. I guess I need one more. So carbon 1, 2, 3, 4, 5, 6. And when you number them, carbons 1, 2, 3, 4, 5, and 6. Now the double bond is on the third carbon. So regular hexene has the double bond on the end. 2-hexene, it's coming off of carbon 2 going to carbon 3. 3-hexene, it's coming off of carbon 3 and going on to carbon 4. And there's still the same number of hydrogens no matter what. No matter whether it's hexene, 2-hexene, or 3-hexene, it's still got exactly the same number of hydrogens. The number of hydrogens is not going to be any different. Just the positions of the hydrogens are going to be in slightly different places. So let's see. I guess I got to get another hydrogen here, another hydrogen here. So that's called 3-hexene. Regular hexene, the double bond is on the end. All right, we'll do some other examples too. But there's also ways that carbon forms rings. And oftentimes, whenever the carbons are in a ring, we also call it an aromatic ring. And you say, well, aromatic, that sounds like, something that smells good or has an odor. And it turns out that many times ringed carbons do have an odor, and many things that are odoriferous or aromatic have aromatic carbons. But it's not always true that things that are cyclical or have rings or aromatic always have an odor, but they're also called aromatic rings. Carbons can end up to form into rings. So the one good example of that is there's a compound where 6 carbons form a ring, where instead of the carbons just being in a chain, like a 6-carbon chain is like that, you can also have a 6-carbon ring where the 6 carbons form a ring. And it turns out that those molecules with 6 carbons in a ring, or any number of carbons in a ring, have the prefix cyclo. So if there's 6 carbons in a chain, and if they're all single bonds, and I guess here I'll include the hydrogens, you'll see, in organic chemistry, we take a shortcut and don't show all the hydrogens coming off it all the time, because it's a lot of hydrogens to draw, and it's assumed that there's hydrogens coming off of it. 6-carbon chain, that's, hexane, hex, 6, and it's an alkane because they're all single bonds. But if there's 6 carbons in a ring, by ring they're all in a circle, the name has cyclo, and then the number hex, and then whether they're single, double, or triple bonds. And because these are all single bonds, that's called cyclohexane. Oftentimes the shape is drawn and no actual carbons. We also have an even bigger shorthand to not even draw the carbon atoms. Instead, sometimes you'll see it just drawn like this, and every time there's a change in direction, every time there's a little kink, that is an indication of the presence of a carbon atom. So this is another way to draw that same structure. With 6 carbons, there's a carbon at each of these little intersections or little directions and joints. If we want it to, instead of having all single bonds, if we want to illustrate double bonds or triple bonds, so if you have like this 6-carbon ring, but there happens to be a double bond somewhere, we can draw the double bond in the ring, but you'll also see it drawn like this, where there's just another line. There's carbons here, 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 and here, but there's a double bond in this location. So this is a real big shorthand in illustrating like numbers of carbons that exist in a ring. I'll show you some examples of those. Oh, there's a slide in the slide deck about things that are true about bonding a carbon to hydrogen. And these are things that are always true. All atoms try to have an octet or 8 valence electrons. Carbons and hydrogens are nonmetals. They always want to share electrons. So they always are involved with covalent bonding and not ionic bonding. Like carbon and hydrogen don't ionically bond. They have covalent bonds between them. Hydrogen only needs 2 electrons to fill its valence electron level. But carbon wants to have an octet or 8 valence electrons. Hydrogen only forms a single bond, but carbon needs to have 4 valence electrons that it picks up. So it has to end up having 4 bonds coming off of it. So what's true about all these rings and straight lines is that we end up having 4 lines coming off of carbons, but a single line coming off of hydrogens. All right, so here are some examples of a couple different cases. Here, let me just slide this over. So the different, this should say carbon. It says carbon correctly in the slide. I don't know why it says carbon there. Just mistype. For example, the different ways that you'll see and to draw structures for alkanes, alkenes, and alkynes, whether they're in a chain or whether they're in a ring, depends upon how much detail the person's trying to show, how quickly you want to draw it, but they all have exactly the same meanings. So, for instance, this thing over here on the left, this 2-butene, this is a good way to draw it. This is the most common way that you would see because it illustrates the presence of 4 carbons, the presence of the 8 hydrogens, and shows the number of double and triple bonds. But because you got to draw a lot of H's and draw a lot of lines, it's kind of a pain to do. But those hydrogens are associated with individual carbons. So what I mean by that is over on this end, these 3 hydrogens here, they're bonded to this carbon. On this end, these 3 hydrogens are bonded to the carbon on the right. And the carbons in the middle each only have 1 hydrogen. So there's a type of structure called a condensed structure. And that condensed structure saves you from having to write as many hydrogens and draw as many lines. So you'll also see these kind of condensed structures where the number of hydrogens that's bonded to the carbons on the end is just shown as like a number of hydrogens. This could also be written, what's actually kind of more common to see would be CH3, CH, CH, CH3. Because we just tend to always put carbon before hydrogen in our like naming scheme, but based upon like how it looks, the hydrogens are on the left, so it's okay to have H3C, CH, CH, CH3. And it turns out that this molecule actually doesn't form a straight line. The atoms themselves don't line up straight. In reality, they have a bent conformation. There's this zigzag shape to the actual molecule, and I'll show you that with both space filling and ball and stick models when we work with model diagrams. But this is another way that you'll see it, where the it's like a zigzag, but it doesn't matter that it's a zigzag. The zigzag helps you see the actual shape of the true molecule, but the number of carbons and hydrogens still appears to be the same. It's also shown sometimes with the C and the H together. A further simplification is every time there's a little kink in that zigzag, that's the presence of a carbon atom. So instead of having to draw the carbon atom, because that line has a kink in it, there must be a carbon here and a carbon here. And because every carbon's got to have 4 lines coming off of it, it's also assumed there's a hydrogen coming off of it. And it can simplify even further down to this. So here's what's really, really cool about structures for organic molecules is we take, watch how long this takes me to draw. We take this thing, gotta keep on going, all that I just drew, and just draw that as just that. These two things mean the same thing. And they mean the same thing because, here, I'll draw it one more time. Because, actually, let me back this up. I'm going to draw it like in yellow. When I draw this zigzag looking thing, every place there's an end or a kink, that must be a carbon atom. And because every carbon atom has to have 4 lines coming off of it, these straight lines must be individual bonds anyway. And this carbon only had 1 hydrogen or 1 line coming off of it. So I got to have some more lines, and those have hydrogens on the end of them. This carbon's got 3 lines coming off of it. It needs another hydrogen. Same with this one. And this carbon over here needs hydrogens. Like that. So now this is looking a whole lot closer to that structure up there. You'll see different variations of structures and formulas for organic molecules based upon how well people are at recognizing what this shape here means and how that relates to numbers of carbons and hydrogens. So you'll see lots of those variations as we go along. Let's see. I guess I got that one in there twice. All right, there's only a couple more minutes left. But at the end of the slide, there's examples of naming individual hydrocarbons with numbers on the ends. There's ethene and propene. In this example, it's 3 nonene. And that's because each of these kinks had to be the presence of a carbon atom. So there's 1, 2, 3, 4, 5, 6, 7, 8, and that's the 9th one. It's 3 nonene because when you start numbering them from the end, that's 1, 2. This is the 3rd one in. The 3rd one in is where the triple bond is. If I wanted to draw 4 nonene, and non-ene means that it's an alkene, I got to have the first carbon, and then 2, 3, and if this is the 4th carbon, that's where the double bond is, then 5, 6, 7, 8, 9. So now I've got a total of 9 carbons in a row. This would never be called 5 nonene, because although you could number from this end, 1, 2, 3, 4, 5, and the carbon, this 5th carbon is where the bond is, you want these numbers to be as low as possible. And because this double bond is closer to the left end, it's better to start naming from the left end. So there actually is no such thing as 5 nonene. That wouldn't exist. But you could have nonene. Nonene would have the triple bond or the double bond right on the end. 2 nonene, it would be here. 3 nonene would be here. And 4 nonene would be here. If you would say, well, this would be 5 nonene, well, that's not true, because when you start numbering from this end, it's on the 4th one in. Anyway, I know that's a lot, and it's a little bit complicated, and it's a little bit easier if we have the model sets that you can actually like physically like manipulate. We'll see how that goes, but in the folder for this week, let me get back to it here. And there's only like a minute left. Let's see, naming hydrocarbons practice. In the folder for the week, down at the bottom, the folder says hydrocarbons practice 2. And this has molecules that, there we go. So this one is just an alkane. This one's an alkene, has 2 carbons. This is one of these ones that has a ring. So it's cyclo at the beginning, and then the number of carbons, and then the end depends upon whether or not there's single, double, or triple bonds. There's another one here with a double bond and the 2nd carbon. This one has that real shortcut orientation. And then try to draw structures for those compounds, 6, 7, 8, 9, 10. And I know that they're going to be tough, but try to get through them and try to get the names as well as you can. And then tomorrow, I'll go over those in detail and give you some more to work on. We'll work on some more together. So, all right, bell's gonna ring in like 8 seconds. So that's what I got for today. We'll do more practice, so don't worry if it seems really super complicated. All right, I guess you got to go